Hello, everyone, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. I'm Ashley Martini. As always, the goal of the seminar series is to bring our community together. The seminars stream live on the third Thursday of every month at 11 a.m. Eastern. They're also available to watch anytime on the YouTube channel. We've had an amazing group of speakers so far as part of our seminar series, and again, you can watch all of these on the YouTube channel. We also have some excellent speakers planned for the upcoming months, and we hope that you will join us for all of them. Before we get started, a few quick thanks. First, Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, Dr. Frankie Antolon, the Center's Outreach and Education Coordinator, and Ryan Kwok, the seminar series student lead. Thank you again for joining us. Please do continue to follow us and join us on the YouTube channel. A few more quick guidelines. Reminder that the webinar is being recorded. If you have any questions, you can either email them to us at cmccdiscussions@gmail.com, or you can post them directly into the YouTube channel. Either way, they will be propagated to the speaker at the end of the presentation. Finally, we do appreciate your feedback and we want to hear from you. So we created a short survey so we can learn more about what you, our viewers, like and make our seminar series even better. You can either use the QR code shown here or click the link at the bottom of the description of this seminar. Again, we look forward to hearing from you. Finally, last but not least, it's my great pleasure to welcome today's seminar speaker, Dr. David Bryce. Dr. David Bryce is a full professor and university research chair in nuclear magnetic resonance and past department chair in chemistry and biomolecular sciences at the University of Ottawa. He previously obtained his bachelor's from Queen's University, PhD from Dalhousie University, and was an NIH postdoctoral fellow. His current research interests include solid-state NMR, low-frequency quadrupolar nuclei, NMR studies of materials, NMR crystallography, halogen bonding, mechanochemistry, and quantum chemical interpretation of NMR interaction tensors. Dr. Bryce is the author of approximately 225 scientific publications and 2 books. He is the editor-in-chief of Solid-State Nuclear Magnetic Resonance and section editor for the Canadian Journal of Chemistry, as well as a fellow of the Royal Society of Chemistry and an elected fellow of the Royal Society of Canada. It's my great pleasure to welcome David Bryce to the Mechanochemistry discussions.
Okay. Hello, everyone. So I'm David Bryce from the University of Ottawa in Ottawa, Canada. And it's a real pleasure to be invited to speak as part of these mechanochemistry discussions. I'd like to thank Professor Martini and everyone associated with organizing these discussions for the invitation. So in the next 30 minutes or so, I'm going to tell you a bit about some of the mechanochemistry work we've been doing in our group. My background and training are more in the area of solid-state nuclear magnetic resonance, so I'll have a focus on those aspects and give you some background on what we do in the group. I understand there's perhaps a diverse audience that attends these seminars, perhaps with some chemistry background, some engineering background, so I'll do my best to try to keep this accessible to a broad audience while also trying to convey, what I think is a very good fit between what's going on in the area of mechanochemistry and what we can do with solid-state nuclear magnetic resonance. So a brief overview of some of the things we do in my group. Obviously, mechanochemistry and solid-state chemistry is one aspect of this, which I'm going to focus on today. But as I mentioned, our main area of expertise is solid-state nuclear magnetic resonance. And I'll touch on some of the advantages of this method in the coming slides. Many of you will be familiar with nuclear magnetic resonance, particularly solution NMR, traditionally used for characterizing organic compounds and all sorts of molecules in solution. There's also a lot we can do in the solid state, as I'll show you. One application of this is something called NMR crystallography, a field where we use NMR data, often in concert with diffraction data and computational chemistry, to solve or refine crystal structures. And this can be quite advantageous, particularly in the field of mechanochemistry, where we end up with powders. We don't end up necessarily with single crystals that we can stick on an X-ray diffractometer, and solid state NMR is very well suited for these types of materials. We have a big focus in our group on quadrupolar nuclei. So quadrupolar nuclei make up most of the periodic table. Those are nuclei with nuclear spin quantum numbers greater than 1/2. So not things like proton and carbon that we're used to looking at in organic compounds, but most of the other elements in the periodic table, and I'll talk a lot about those today. Also touch on some nuclear quadrupole resonance, which I'll explain later. And we have a lot of interest in looking at non-covalent interactions, both with solid state NMR and with mechanochemistry. I'll touch on some of those. There's some other areas on this slide mentioned about what we do in the group. So in general, our approach often involves, preparing compounds if we're not collaborating with people. So doing some crystal engineering, doing some mechanochemistry or simple co-crystallizations. We're not necessarily synthetic chemists. And then we make use of the tools available to us, including X-ray crystallography and multinuclear solid state NMR, as well as computational chemistry to characterize these compounds, which are of interest to us for one reason or another. I'm showing you some nice pictures on the right there. These are actually prepared using cosublimation, which is, I would say, not quite mechanochemistry, but mechanochemistry adjacent, whereby we're preparing known and novel co-crystals and compounds in the absence of solvent or heat or anything like that. So I'm going to touch on various aspects of our approach today, as I say, incorporating obviously mechanochemistry, diffraction, multinuclear solid state NMR, not too much computational chemistry in this talk today, but it gives you an idea of the scope of tools that we use in our work. Okay, so why solid state NMR? This is a mechanochemistry discussion. So as I mentioned briefly at the beginning, so NMR in general is generally a non-invasive, non-destructive type of spectroscopy. Okay, so we can put in a sample, we can recover the sample. Okay, typically with solids, we're looking at powdered samples. They don't have to be well-ordered materials, but we pack these usually in a 4mm rotor. Magic angle spinning NMR to get high resolution spectra. We can recover the sample at the end. The method is multinuclear and site specific, meaning that we're looking at individual types, isotopes in our system. So site specific information on different functional groups, non-covalent interactions, that sort of thing. So we can really get local structural information in contrast a little bit to what you might get from diffraction, which is a longer range average picture. We can get longer range crystal packing information. So in this sense, solid state NMR will be sensitive to things like polymorphism and hydration, just like diffraction is. But one of our big advantages, as I've alluded to, is the ability to look at disordered and amorphous samples with solid state NMR. So we're still able to get this kind of site-specific spectral resolution of resonances, even in cases where you may get a broad lump in your powder X-ray pattern. And of course, in principle, there's no purification or workup of samples required. Obviously, whether your sample is pure or not depends on what you're doing, but you can just pack anything you want basically in the NMR rotor and get some information. And again, no single crystals required. So all in all, I would say this is a great fit for looking at and understanding mechanochemical transformations. And I know Danielle Laurencin has given a talk a while ago in this discussion series, and she's another solid state NMR researcher who's really doing a lot with solid state NMR and mechanochemistry. So one of the things we're interested in the context of mechanochemistry and solid state NMR is looking at non-covalent interactions. And depending on your background, you're probably familiar with things like hydrogen bonds. These are things, interactions that hold together co-crystals in the solid state, very important in pharmaceuticals and that sort of thing. We're interested in these other classes of sigma hole interactions. So the prototypical example is the halogen bond. So at the top there, I've got 4 electrostatic potential maps. And as you can see, as we go from left to right in CF4 through to CF3I, you can see on the iodine on the right there in red an area of elevated electrostatic potential and decreased electron density. So despite the fact that this heavy iodine atom has a lot of electrons around it, The CF3 electron withdrawing group creates this so-called sigma hole, which can accept electrons and form these non-covalent bonds. And there are some analogous classes of interactions, for example, the chalcogen bond, the pnictogen bond, or you can see below here the formation of 2 or 3 in these cases, sigma holes, and these can interact with electron donors to form cocrystals and that sort of thing in the solid state. So this has really been one of our focuses, both from the mechanochemistry perspective and the multinuclear solid state NMR perspective, because you can see the range of elements here involved in these classes of interactions. We're not just looking at things like carbon and hydrogen. Okay, so the tools that we have accessible to us in our lab, obviously things like mortar and pestle. We have a standard Retsch mixer mill, ball mill. A few years ago, we were able to get the Pharma 1 Resonant acoustic mixer. This is one of my students, Ali here, who's been heavily involved with the work we do. And some smaller tools like vortexers, a dental amalgamator for trying to set up some specific types of in-situ monitoring of mechanochemical reactions. And so one of our interests was in, exploring the formation of some of these non-covalent interactions using resonant acoustic mixing, or RAM. So classes of interactions in cocrystals that have been studied quite extensively, both by solution chemistry, but also, in the past decade by ball milling. And we wanted to explore the potential of RAM in this context. I did mention cosublimation at the beginning. I just wanted to touch on this. Was another thing that we did about not quite a decade ago, but this idea of using cosublimation of pure components in a vacuum tube we found was a very interesting way to get highly pure single crystalline materials in the same kind of way that we can do with mechanochemistry. So just another kind of, as I say, mechanochemistry adjacent tool that I find quite interesting to look at. So here's an example of one of our mechanochemistry studies analyzed by solid state NMR. So what I'm showing you here, the bottom left are some of the compounds that we're looking at. So compounds 1 and 2 are halogen bond donors. These are iodoethinyl substituents on some aromatic rings. And the iodine at the end of this triple bond can form that sigma hole, as I mentioned, and act as an electron acceptor, in this case, forming halogen bonds with either the chloride or bromide anions shown in the molecules or the salts on the right. And we prepared these cocrystals using ball milling, so pretty standard conditions. I don't have the conditions up on the slide here, but the point here is to show you kind of what kind of monitoring capabilities we can get with solid state NMR. So again, with no kind of workup, no purification, no growth of single crystals. The top left here, I've got carbon-13, cross-polarization, magic angle spinning NMR spectra. So these are spectra of the powders that come out acquired with fast magic angle spinning on the order of 10 kilohertz to give us high-resolution carbon NMR spectra analogous to what we would see in solution. But of course, we're looking at our intact solid products from the ball mill. And on the left, for example, for donor 1, we have a spectrum here. And you can see the 3 stacked above here, for example, cocrystals 1A, 1D, 1E. We get clear differences in the spectra, okay, attributable to obviously some change in the crystal packing, in this case, the formation of a cocrystal. We can zoom in on particular peaks, for example, the alkynyl carbon, and monitor very clear, changes in that chemical shift. So a way to very clearly see product formation, and also a way to assess purity, because we have no overlap with the starting material. And of course, we do this all in conjunction with diffraction when possible, but I'm highlighting most of the NMR aspects today. In the middle here, compound 2, just a different donor, showing you another example of the same thing, showing you the different spectra we can get upon mechanochemical formation of these halogen bonded cocrystals. On the bottom right are similar types of spectra, but this time for phosphorus. So you can see in these salts on the right here, we have single crystallographically unique phosphorus, for example. And so those phosphorus spectra on the right here are much fewer peaks, less overlap, and clear shifts in the spectra, clear changes in the spectra when you form these cocrystals mechanochemically. And in some cases, in this case, we were able to actually grow some single crystals that match the powder or X-ray diffractograms. And a lot of our initial work was trying to see what we could do to reproduce known crystal structures that are available from solution. Of course, we then move on to see what we can do that's new. So I just wanted to highlight kind of the nature of some of these structures. They form very interesting halogen bonded networks. And again, on the left here, just emphasizing kind of the clear shifts that we see upon co-crystal formation. So the bottom trace would be our phosphorus resonance for our pure starting material. The top trace here, we have formation of a co-crystalline product, and you can even see now a trace of starting material left over. So very easy way to quantitatively monitor what's going on as a result of your ball milling. Okay, so as mentioned, we're interested in these halogen bonds. There's been a lot of work on these types of co-crystals done over the years with solution chemistry and also with ball milling. So we thought, well, can we make these using RAM? Many of you know that RAM is a slightly different technology, where we're not bashing ball bearings and that sort of thing into the powders, so perhaps a somewhat less harsh technique. But we nevertheless wanted to see, can we make halogen bonded co-crystals in this way, both dry and perhaps with a couple of drops of liquid added. So we wanted to essentially establish whether this was possible. And so my student Ali set out to do this. One of the first projects we did when we got our RAM instrument, and it was quite a success. So I'm showing you on the left here some of the donor molecules 1 and 2. These are prototypical halogen bond donors. And then a series of electron donors, A, B, C, D, E. In these cases, these were mostly co-crystals with known crystal structures. So the question was, could we reproduce what was known with RAM? And we have powder X-ray diffractograms here. So you can pick a couple and look by eye here, the calculated trace from the single crystal X-ray structure, and then what we're able to get with RAM. And in basically all of these cases here, most of these cases, we get kind of bang on what you would expect. We can also then, in this case, use fluorine-19 solid-state NMR. So those are the traces on the right-hand side, because our donor molecules 1 and 2 have fluorine nuclei in them. This is a very sensitive probe nucleus, so we can get these spectra in a matter of a few minutes. And again, if you just take an example here, so at the bottom, we have a pure donor paradiodotetrafluorobenzene. This is the fluorine spectrum. I hope you can see my mouse. Anyways, bottom trace here. And if we prepare a certain co-crystal 1A by ball mill, we get a different spectrum. By RAM, we get the identical product. And you can look through by eye, and most of these are perfect matches, basically showing that yes, with RAM, we can reproduce exactly what we're getting from ball milling. There are a couple of interesting traces where we see some differences. So for example, if we look at 1C, the ball mill gives this trace, RAM gives this trace. So this may be attributable either to a different polymorph being formed, or perhaps some impurities left over. If you look carefully at some of these traces, don't know if there's a good example on this slide, maybe on the next slide. I'll show you on the next slide. There's some differences in the crystallinity that we can pull out from the RAM products versus the ball milling products. So this is more spectra, carbon-13 spectra now of the same types of co-crystals. And so this is a tetramethylpyrazine carbon-13 spectrum at the bottom left. We prepare co-crystal 1A. We get this trace with ball milling and with RAM, same product. In this particular case, we have a second polymorph 1A2 prepared with the addition of a small amount of solvent. And you can see there's actually a small shift in these peaks, indicating that we're able to get a different polymorph now with RAM by adjusting the conditions used, a polymorph that we're not able to get from from ball milling, sorry. And if you look at the top right, for example, product 2B, you can see the trace from the ball mill, the trace from RAM give essentially identical spectra, so the same product, the same polymorph. But if you look closely, you can see that actually the spectrum that we get from the RAM product has a bit better resolution, has a bit sharper peaks here, both in the middle peak and on the left. And this is a measure that we're getting better crystallinity from the RAM product. Okay, so perhaps a degree of amorphization coming from the ball mill. So RAM is really a useful, not too harsh method to produce known and novel halogen bonded co-crystals that sometimes we can get with the ball mill, and sometimes we get new polymorphs. So that kind of sums up this little section here looking at these halogen bonded products. So again, a few more examples here of carbon-13 spectra. Again, at the top right here, 2E, another nice example where we get the same product with ball milling, but clearly better spectral resolution in the RAM product, indicative of higher crystallinity in the RAM product. And again, on the right here, when we're able to, what we try to then, once we've prepared these mechanochemically, we see if we can grow single crystals that reproduce the diffractograms and the NMR spectra. Sometimes we can, sometimes we can't, but nevertheless, it's interesting to look at the halogen bonded networks in these systems. So the next question was, can we make chalcogen bonds with RAM? So to remind you what a chalcogen bond is, we're looking at a group 16 element like tellurium. We have the formation of 2 sigma holes, so areas where we can have non-covalent bond formation opposite each of these tellurium-nitrogen covalent bonds. And these had not been prepared before with RAM and not really with ball milling either. And so we were kind of intrigued by that. They've been prepared with solution chemistry. So what is our motivation? As I've explained here, both in our lab and from hearing from other people, that when trying to use a ball mill on these types of donor molecules, we found that the ball milling was too harsh, at least in the case of donor molecules like this, meaning that we'd get decomposition of that molecule even when trying to use gentle grinding conditions. And it was just not a good route to get these cocrystals. So we thought, well, RAM might be less harsh. Maybe we can do something here and find a new way to make known and novel cocrystals without solvent. At the same time, in this paper, we built a little tool to help with automating some of our RAM experiments, which I'll touch on briefly. Okay, so this is the problem that we had encountered. So again, this donor molecule here, kind of past efforts from our group, we're looking at trying to make cocrystals of this, but we just kept getting either impure products or amorphous products, not things that we could really use. And so if you look at ball milling, just a pure donor molecule by itself, you can see, okay, time 0, a nice sharp, this is a powder X-ray diffractogram. But after just 5 minutes with standard conditions, so 5mm balls, 20-30 hertz, we can see there's a lot going on here. We have some either degradation, amorphization, and or both, and this happens pretty quickly. When we looked at RAM, though, of the same molecule, you can see on the right here, even after 2 hours, it does not degrade this donor molecule. And so we thought, okay, this is good. Maybe we can do something with RAM with this molecule without it falling apart. Okay, and indeed we were able to do that. So we looked at a whole series here of trying to make these cocrystals of this fluorodiazole, again with chloride and bromide electron donors in this particular case, and we went through a whole series of conditions described in one of these RSC mechanochemistry papers. So powder X-ray traces here of 1, of A, and then various products under different conditions. And if you look carefully, I mean, in this case, through one of these trials, 2 or 3, we're kind of able to get the best agreement. In this particular case, maybe not complete conversion, comparing to 1A sim is the actual single crystal trace. So in this case, we were able to get the product almost in every case, regardless of the conditions used. So this was promising. Same thing with another molecule here. There are 2 known polymorphs of the cocrystal 1B by varying conditions. So different solvents, different amounts of liquid added, different molar ratios, etc. In no case do we get this second polymorph, 0, 1. But by adjusting the conditions, we can get the first polymorph, DOP SEK, perhaps best in trace 1B5 here. Okay, again, just by adjusting conditions, you can see it's quite sensitive exactly to what we put in. Another example here with 1 and C. Again, here's what is simulated, what we expect from a single crystal study. And in this case, again, pretty convincing conversion. In most cases, there's some leftover impurities, but again, we can pick out the one here that gives us the best conversion, the best conditions. And this is just a summary of some of these optimized RAM conditions for these cocrystals. So the first time that this has been done with RAM, or I think really with any kind of mechanochemistry to make these cocrystals with fluorodiazoles. And this is just a table summarizing some of the optimized conditions. So interestingly, you can see a range of different liquids were needed, and in some cases, or at least one case, no liquid actually gave the purest conversion. And powder X-ray diffractograms on the right here kind of represent the best that we're able to get. So we have experimental and simulated traces there, and they're all in quite good agreement. And I'll point out here that the time in the RAM here was up to 90 minutes. So in the Pharma RAM 1 that we have, the firmware controls us to running up to 5 minutes only, which has been useful in many cases, but we found that much longer RAM times were necessary in this case. And so just as a little side project here, my student designed a little robot to basically push the button every 5 minutes and 1 second. I understand there's probably some commercial robots you could buy to do this, or I could buy a bigger Pharma RAM, but I thought this just was an interesting little tool that my student made. This is just a very short video showing how he sets it up, and the robot will press the button, and so we can set up, runs for 60, 90 minutes or even longer without having to, buy new firmware or that sort of thing. So it's just keeps running without having to stand there. There. If you look carefully, you see the button being pressed. So that was kind of interesting, and if anyone's interested in that, that's all in the Mechanochemistry paper, where how to build this little robot and the code and that sort of thing. Okay, in the final few minutes of my talk, I want to get back a little bit to NMR and the idea of looking at these so-called quadrupolar nuclei. So you'll notice that some of those initial halogen bond donor molecules that we're interested in contain things like iodine, and as we'll see, bromine. These are not elements that it's easy to do NMR on. And that's one of the reasons why there's always the push for higher field magnets in NMR. So we're up to, for example, a commercial product now from Bruker, 1.2 gigahertz proton frequency. And one of the big reasons for this push, as I say, is for looking at these strongly quadrupolar nuclei, where the signal to noise really goes up with the strength of the magnetic field, and the lines get much narrower with the higher fields, thereby increasing spectral resolution. I'm probably not going to go too deeply into this, but I wanted to mention also the concept of nuclear quadrupole resonance. So nuclear quadrupole resonance is essentially, let's just get rid of the magnetic field altogether and allow our spin states to be governed by the quadrupole interaction itself. But without going into all these details here, that's kind of what we're doing here, is instead of trying to push to the highest fields possible, let's just turn the system upside down, go to the lowest fields possible, and we're actually going to recover some of the spectral resolution that we're looking for. I wanted to highlight here, this is a paper that just came out a day or two ago, where we use the concept of nuclear quadrupole resonance and Zeeman perturbed nuclear quadrupole resonance to look at the results of some mechanochemical reactions. So this came about, we were trying to prepare some ternary cocrystals via ball milling. Okay, so the compounds here are listed. So again, our perfluorinated iodobenzene, perfluorinated dibromobenzene, and a bipyridine donor molecule. So we've got iodines and bromines in these molecules. We're trying to form cocrystals with mechanochemistry and monitor what's happening. So what we found was that we didn't get our ternary cocrystal. We actually got a mixture, an impure mixture, or a physical mixture of things. But using this NQR and Zeeman perturbed NQR approach, we're actually able to get quite good spectra that we can interpret for these very difficult NMR nuclei like iodine and bromine. So what I'm showing at the top here is nuclear quadrupole resonance spectra of mechanochemically formed cocrystal 3A. Nice sharp peak. There's actually 2 peaks. Same for pure compound 3, 1A, and 1. Okay, so all very well resolved, very easy to do, despite the fact that these are difficult nuclei. Again, no purification needed. You can take it right from the ball mill or whatever. And in B here, this is using a small magnetic field to perturb these line shapes, and we're actually able to assign all the resonances from all the products and see, okay, we have this proportion of cocrystal 3A, we have this proportion of cocrystal 1A, and we have some leftover starting material, compound 3. And all using this kind of, It's not a new kind of spectroscopy, but it hasn't really been used in this context in recent years. I really think this is an interesting potential way to look at mechanochemistry, perhaps even in situ, because with nuclear quadrupolar resonance, we don't have to have complex magic angle spinning. It doesn't need to be inside a large magnet to do this kind of spectroscopy. A lot more freedom to set up the way you do the experiment. So we're pretty excited about this. So easy to look at physical mixtures, cocrystals, all sorts of things, looking at very difficult elements. Okay, I still have a few more slides. In the last little section, I want to look at some in situ aging processes or pressure-induced solid-state transformations. So as I mentioned, NMR is generally non-destructive, but it turns out in some cases, we're able to observe some transformation in real time. So you may have polymorphs that transform as a function of time, either just because of time or the humidity in the air or the temperature or the pressure. So we can look at perhaps polymorphic transformations, aging reactions or transformations, and in favorable cases, maybe some covalent or non-covalent chemistry, which of course we can monitor using other spectroscopic techniques if we have the right setup using mechanochemistry. So as a proof of principle, we were looking at the formation or what happens to this co-crystal between triphenylphosphine oxide and iodo-fluorobenzenes, and again, looking at a halogen bonded system. So to start, we've got our triphenylphosphine oxide and 3 different donor molecules here. And we're able to get single crystal structures using regular solution methods. And this is basically just to see what we have from the crystal structures. And then we try to monitor if we can make the same forms mechanochemically. And as I mentioned, this type of real-time monitoring has been done before. So there's a nice example here using solid-state NMR, just looking at a sodium acetate, a hydrate, and you look at what happens over time with your spectra, and the dehydration of that hydrate gives rise to 2 different polymorphs of sodium acetate. Tomislav Frischik has also done a lot of real-time studies with various types of spectroscopy and diffraction to do the same type of thing. So we're thinking, what can we do with NMR or NQR spectroscopy? So my former student here, Colette, worked on this project where we took pure powders of triphenylphosphine oxide in our halogen bond donor molecule. We place these powders in a vial, perhaps with a drop of liquid, vortex them quickly to mix them, and then put them in our magic angle spinning probe and monitor this reaction in real time, so formation of cocrystals. Okay, there's some information here on the single crystal structures, which we always obtain ahead of time to know what we're looking at. And in this case, as I'll show you, what she's able to see was the formation of 2 different polymorphs, 1 and 2. So the formation first of polymorph 1, and then its conversion to 2 in real time. So here's an example of this phosphorus 31 NMR spectrum that we get. So at time 0 is the blue or cyan trace at the bottom. We just get a peak for our triphenylphosphine oxide. If we do what we're calling time 0 with 3, 4, or 5 microliters of acetonitrile added, we can see already right away formation of product 1. And with 5 microliters, already a little hint formation of product 2. Okay, so a whole bunch of series of experiments were done here. Without liquid, with 3 microliters of liquid, 4 microliters of liquid. We can do this at different temperatures. We can do this at different magic angle spinning rates and monitor what happens in real time. You can see at the bottom left here, this trace. So we've got various different variables here to monitor. I'll note that the pressure in the wall of the rotor at these spinning speeds is estimated at 50 to 100 atmospheres. Okay, so we have perhaps obviously some sort of pressure acting on the material as opposed to just the aging in the air. And by analyzing these data using various possible solid state models, we can fit the data. And in this case, we get a diffusion controlled model, 1-dimensional diffusion in most cases. The best fit was 3-dimensional with more liquid added. There's a bunch of plots here I'm not going to walk through, but we analyzed all these data. And we were able to get out an activation energy for the formation of this halogen bond, albeit with a large error. But nevertheless, I think probably the first direct kind of measurement in the solid state in real time between these two powders forming the halogen bond as you're doing the NMR experiment. So I think that's half an hour, 35 minutes or so. And I've tried to touch on various different aspects here without going too deep into the NMR, but I hope I've given you a glimpse of some of the things we can use solid-state NMR for to study mechanochemical reactions. I'll just emphasize some of the points I've made. So again, single crystals are not needed. We can look at amorphous samples. You get really distinct fingerprints for different polymorphs, just like with powder X-ray. We can look at kinetics for real-time reactions in the NMR rotor. And obviously this is complementary to diffraction methods. And I would say, the real plus for NMR is the site-specific monitoring of specific isotopes, the ability to get really well-defined spectra even for amorphous samples. And it's also very easy to study dynamics, which I didn't touch on today. I've shown you we can form and monitor non-covalent interactions like halogen bonds and chalcogen bonds using not only ball milling, but also RAM. And I touched on nuclear quadrupolar resonance, which is another spectroscopic handle on mechanochemical transformations with really difficult nuclei that we can't look at with traditional NMR techniques. I will conclude there. Thank the funding agencies. Ali here is one of the main students who's done the work I spoke about today. Tio has also been involved with this work, and some other people who have moved on from the group. I think that's a good place to stop, and I'd be happy to hear any questions.
Thank you very much for your presentation. We have a few questions here. Earlier in the presentation, you mentioned higher crystallinity with RAM. Is there a way to quantify how much better the crystallinity is using the data that you showed?
Quantify, I suppose what I would say is, by NMR alone, I'm not going to be able to give you, for example, a crystallite size, but if you have a reference material, for example, pure starting materials that you know are well behaved, or you might know the particle size directly from SEM or something like that, you would expect then the line widths to be comparable for materials of similar crystallinity. But kind of what I showed today was more qualitative. So you kind of get a handle, experience for, crystalline materials give line widths that you can reproduce in solid-state NMR. You see things that are broader than that, then there's some degree of disorder, but I can't put a number on it from the data I've shown you.
All right, thank you. All right, I received a few different questions about this, and I'm going to kind of distill into a single question that's about the difference between the RAM and the ball milling.
Okay.
So I think maybe if you could describe a little bit more about why they're different. And then there was a specific question about the difference that you mentioned in the severity of the milling. So if you could touch on that point as well.
Sure. I'm sure there's experts in this discussion that know more about this than I do, but so ball milling, you've got, at least in our case, you've got a stainless steel jar with stainless steel balls. You can use different types of materials for the balls in the vessel. But basically you've got a hard ball smashing into your compound, into your crystalline material or powdered material, creating defects, adding kinetic energy to allow some sort of transformation or reaction to happen. But you have these heavy balls that are smashing into your powder and certainly causing things to happen. So there's a lot of kinetic energy involved. And I think it's known that, if you do this for too long, you may get your product, but it's going to start to become disordered. You're going to crush the crystals, perhaps introduce some degree of disorder. With RAM, the standard setup is there's nothing in there except your compound. You could add things, I suppose, to increase reactivity. I know that's been done, but the standard setup is just your compound, your powder in a vial, and the transformation is induced by essentially vibrations, the standing waves induced by the RAM machine. So it's basically the particles themselves are colliding with the wall and with themselves, and energy is being afforded through these vibrations in the RAM machine. So you don't have this direct kinetic energy of the balls smashing into your particles, making them more amorphous, into your compound, making it more amorphous. And so at least from what we've seen, in certain cases, the RAM has enough energy or does the trick to cause the co-crystal formation that we're looking for without degrading the crystallinity of the materials too quickly.
Thank you. The next question is, would in-situ SSNMR using RAM be feasible?
No. So for a few reasons. First of all, I mean, the RAM setup is quite big. So with solid state NMR, the problem is with NMR is everything is in a magnet with a very small bore. So even if you're not spinning the sample in NMR, there's not really room to get that into the probe. This is why I mentioned the possibility maybe of in situ nuclear quadrupole resonance, because nuclear quadrupole resonance, it has the same type of probe, but there's no magnet. So there's no confines on the space around the coil that holds the sample. So there's maybe more potential there, but in the terms of the way RAM works, I'm not so sure because, yeah, I think, ball milling probably has a better chance because I can imagine shaking something back and forth within the coil with some sort of non-metallic ball inside might have some potential.
Got it. I think that we have time for one more. Let's do one more question here. I noticed that your in situ solid state NMR experiments used liquid reagents. Have you achieved any in situ NMR with reagents that are powders?
So, I mean, in this case, the answer is yes. In this particular case, you can see, for example, with 0 microliters of liquid added. So remember, this is in situ NMR with no grinding, no anything, right? We're just spinning the sample. There's some added pressure. But even with 0 microliters of liquid in that case, you can still see a transformation. It's slow, but it's happening. So the reason we're adding liquid in this case is to try to speed things up a bit. So I think that's the only in situ NMR experiment I showed. The earlier examples were ex situ, and yes, there were examples there with no liquid added.
Great. All right. Thank you very much for your presentation.
Thank you.
Thank you so much, Professor Bryce, for that outstanding presentation. And thank you so much for joining us. Just a reminder that we've had an amazing group of seminar speakers over the past few years as part of this seminar series, and that you can watch all of these on the YouTube channel. And finally, we do want to hear from you. So if you have any input, suggestions, feedback for the seminar series, we would be more than happy to incorporate them to improve the offering. Please go ahead and use the QR code here, or you can click the link at the bottom of the description of this seminar series. Thank you ahead of time for your feedback. Finally, we have some upcoming speakers planned for the months ahead, and we hope that you will join us for all of these. Thank you again.